Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's our great pleasure to have Professor Chen Zhang from Hong Kong University of Science and Technology to come to Microsoft Research and give a talk on spectrum usage understanding and dynamic spectrum sharing. Professor Zhang joined Hong Kong UST in September 2005 as an associate professor. She is now the co-director of Hong Kong Huawei Innovation Lab and associate director of Digital Life Research Center of Hong Kong UST. Before that, she was with Microsoft Research Asia from July 1999, where she was the research manager of wireless and networking groups. Dr. Zhang has won a number of prestigious awards, including TR 100 from MIT Technology Review. She received the Best Asia Pacific Young Research Award from IEEE Communication Society in year 2004, received the Best Paper Award in MMTC in 2005, Best Paper Award from QSHA in 2006, GlobeCon 2007, ICDCS 2008, and ICC 2010. She has been elected as the IEEE Communication Society Distinguished Lecturer from January 2010 to December 2011. Professor Zhang is also the editorial board member of a number of IEEE transactions, and she was the chair of Multimedia Communication Technical Committee of IEEE Communication Society from 2008 to 2010. And without further ado, let's hear what Professor Zhang has talked about.
Thank you. Thank you, Jing. First of all, let me take this opportunity. Thank you, Jing, for the kind host. It's really my great pleasure to come back to this campus after 5 years. I still vividly remember I was here in 2005. Before I left Microsoft, I'm still visiting different research group and also the product team to do the product transfer. So those are very nice experience for me. Okay, so today I'm back to this place and hopefully deliver some of the recent study in my group. So the title of this presentation will be Spectrum Usage Understanding and Dynamic Spectrum Sharing. So this is the very brief outline. So first of all, share some of the background, and then we're talking about the spectral measurement and the usage mining we conducted. And then after that, by the understanding of the spectrum usage, we're trying to check whether we can do some special interesting thing about the spectrum sharing among the multiple primary users. Finally, will be the conclusion and some of the other directions under my group. So I think most of the audience know pretty well about the background, which is that by year 2020, there will be trillions of wireless devices. All those wireless devices, they want to talk. Not necessarily want to talk to all of them, but they need to talk in a wireless way, so which cause a lot of challenge for the spectrum efficiency in the way that which spectrum we can use and the interference, how can we avoid it, how can we achieve rather good performance, etc., etc. And this also brings a lot of challenges to the network architecture design. Okay, so we're clearly seeing that for the future wireless network, it will need 100 to even like 1,000 times of increase in terms of the radio density, in terms of the bit rate of the radio. Okay, so all this actually motivates us think about the better coordination way, the way to coordinate spectrum usage. And so if we still stick with the current static allocation method, which is a lot of government use nowadays, like US FCC, like Hong Kong OFTAR, and all those places, they use this fixed allocation for the spectrum usage. You run a TV service, I give you a certain fixed band. This band will be used by you for this particular location, and the other people cannot use it. Okay? If we still use this static allocation method, we'll definitely see, lack of spectrum for the future service, future wireless application. So most of you may see this graph many, many times when we're talking about lack of spectrum. This is a typical graph that US FCC actually distribute in terms of their allocation map for different services. And all these colorful things indicate that the spectrum we have has been almost allocated. And if we're talking about future service, 4G, 5G, and all those fancy new services, we may not have enough spectrum. And this one is the similar graph has been disclosed by Hong Kong government. This is after they announced the spectrum allocation map for Hong Kong. The similar trend you can find out. Okay, and this is more particular looking at IMT service, and this has been announced that by 2020. And if we're looking at the spectrum requirement, this is a kind of prediction based on different user demand, whether this user demand is low or high, you will see that we are not have enough spectrum to serve the IMT service. Okay.
What's the source of that?
Yeah, the source actually you can see from here.
Okay.
And a lot of people already did research because we are lack of spectrum, so people seriously looking at the usage of the spectrum. Okay, so you may already see this graph again many times. This is the one distributed by DARPA, and this is the one distributed by Share Spectrum, which is a company doing a lot of measurement for the spectrum usage in US. And they give the similar conclusion in the way that in US, actually, a lot of the spectrum has been underutilized because of many services may not be run all the time, may not be run all the places, so that's why the spectrum usage is not high, okay? So that's why with such a background, with such an observation, people starting talking about new research paradigm, which is dynamic spectrum access. So for dynamic spectrum access, basically, besides the traditional so-called primary user, who is the license holder, and they can use the spectrum when they want. But because they are not use the spectrum all the place, all the time, so that's why this gives the opportunity for the so-called secondary user, which is the intelligent user, they can use the spectrum opportunistically when the spectrum is not being used by the primary user. Okay? So this gives us an opportunity, and also in terms of the entire system goal, people talking about we want to maximize the spectrum utilization, but minimize the interference to the primary user because they are the license holder. So people talking about a lot about the enabling technology, which is cognitive radio, which has the capability to share the spectrum in an opportunistic manner. Okay? So this is the general spectrum management framework. A lot of people has done a lot of research align each direction. Okay? So the fundamental here is that we have a radio environment. So we want to understand the radio environment in an accurate way so as can help us doing the spectrum sensing. I need to know where is the primary user, whether the primary user will back, so as I need to leave the spectrum to the primary user. If I have a very good understanding about the radio environment, then this can help me to do the spectrum decision. These are the spectrum now available, but it may not be available in a short period of time. So that's why I cannot use that. Because once I use that, this is an opportunity, but just an opportunity for a short period of time. And so with the good understanding of the radio environment, we can do good sensing, we can do good decision. Once we have a good decision, we have a good way to share the spectrum, and then this will again affect the radio environment. So that's why in today's talk, I want to particularly emphasize on two topics. One is the understanding about the spectrum usage, which is the radio environment. So we did some spectrum measurement and then some understanding about the spectrum usage. And after that, I will come another topic, which is by understanding about the spectrum usage, what can we do? Okay, so we have a spectrum sharing among the multiple primary users. This is another topic. Okay. So the motivation of this work doing the spectrum measurement is very clear in the way that we see Share Spectrum did a lot of measurement here and there in US. what is the spectrum usage in China, particularly? And we only find out the conclusion people give out, say, well, the spectrum is underutilized. The spectrum is underutilized in China. The spectrum is underutilized in US. The spectrum is underutilized in Europe. But is there any correlation we can find out among the spectrum usage? If there is a certain correlation we can find out, then we can leverage those correlations, helping us to do the spectrum prediction. And this will, again, helping us to do the better decision in terms of spectrum sharing and spectrum access. Okay? So understanding the usage of the spectrum is not only to claim spectrum is underutilized, but we want to do a little bit further in the way that how can we more efficiently access the spectrum. Okay, so that's the purpose, and this is the work we have been conducted, and this is the measurement we conducted in China with the collaboration of the government in China, actually the counterparty of FCC in US. We conduct four, let's see, this can't work, okay. We conduct four measurement. We conduct the measurement in four measurement sites. Two places actually is in the downtown region, and the other two places actually is in the suburban region. And the measurement period actually is last year, 2009. And the frequency band we measured actually starting from the 20 megahertz to 3G. And this actually has been published in last year's Mobicom, and if you want to see some detailed measurement result, you can see from there. And this is the basic information related to the measurement equipment. So the four sites, we use the same spectrum analyzer, which is rather strong spectrum analyzer. It can scan the frequency region from 20 megahertz to 3.6 gig. And the measurement resolution is 1 per like 200K hertz. And then for each round, scanning all this frequency band, for each round, it takes 75 seconds. So we measure that with such a resolution every second, 75 seconds. So eventually we get those measurement points.
Can you back up?
Yeah, sure.
So, okay, so it's over 7 days. Okay.
Tim, a question.
Yeah.
I mean, this measurement individual can take, right? I mean, you don't actually doesn't need a FCC approval for measurement alone. Is that right? Or?
Yes, you are right in this way. But then for this particular measurement, why we need to collaborate with the government? Because we need a very strong antenna to support this type of measurement. And those measurement stations, actually, they have such an equipment. So that's why we collaborate with them, share their resource.
Is this ground level or just above?
And actually, it is above. And you can see this is a typical antenna we use.
Okay.
And around all those spectrum band, we did a measurement. So those are the typical services conducted in China, including CDMA, GSM 900, GSM 1800, and then broadcasting TV band, and also ISM band. And this is a general graph show you the very basic understanding about the measurement. So this is the energy level overview for a certain location. This is a location 3 over the 7 days. And by just a simple view, you can see that actually the energy level for all different services is not that high. So generally tell you that the utilization is not high at all. And then we want to see more detail about this because this is any energy level information. Then we're looking at the real information which is useful for us, which is the channel state information. Okay, so we want to convert the power level to the channel state information. So we want to indicate for a particular channel, if it is idle at a particular time, then that we will indicate the CSI value as 0. Otherwise, the CSI value will be 1. So then we do the conversion. We convert the energy level to CSI data. And the conversion we use, actually, we just simply set a threshold. This is the same similar method we use as shear spectrum used. So we just set a threshold as 3 dB higher than the minimal value you can see for this particular period of time for this channel. Okay. So after that, you can get such a information. So roughly, you can get a similar idea. The spectrum is really underutilized.
Question: when you say the minimum value seen in This channel, is that the 0.2 megahertz channel bandwidth, or basically it's a wider channel?
No, it's just a 0.2.
If it's 0.2, then even some of the frequencies, how come some of the frequencies basically is all blank? I mean, I would expect some fluctuations. So
Because there's some channel actually, basically there's no service. Yeah.
So the dark lines are what would be broadcast, cellular, CDMA, and then GSM. Is that?
And so those places you can see those are GSM 900.
Oh, okay.
And those services are GSM 1800.
Right. Okay.
So I guess Jin's, if I understand Jin's question, I have the same question. So even the difference between the background noise level between day and night should be higher than 3 dB. So even if the channel is blank, when you do the minimum and then put a threshold at 3 dB, you should get activity during the day if the channel is active.
No, if you set the minimal as the basic benchmark, and then 3 dB higher as the case that there's some activity, and then in that case for most of the spectrum, because there are no service running on top of it.
I know, but even if there's no service, there's noise.
But the noise level actually is not that significant.
Doesn't vary 3
Yeah,
dB?
it's not that significant. It's not higher than 3 dB from our measurement testing. And for those first conversion, we gather channel state information, but those state information is for particular time slot. But for the channel usage, what we care more is about the channel vacancy duration. How long this channel can keep idle. In that way, later if I know this information, I can do more efficient spectrum access. So that's why we're particularly looking at the channel vacancy duration. So you can see we got the raw data in energy level, then we convert to CSI series, and then we further convert to get the channel vacancy duration. And then we need to check whether the channel vacancy duration follow any distribution. Okay, so at least a lot of paper when they made a theoretical or whatever simulation study, if they want to understand or they want to make an assumption about the channel usage, most of them believe this is a one-state first-order Markov channel. Okay, so they basically make such an assumption, but then we need to seriously look at whether those assumptions are true or not. Okay, so that's why we check the channel vacancy duration, and we find out this channel vacancy duration follow an exponential-like distribution for all the channels we study, but they are not independently distributed. Okay, so we just do the simple approximation for all the measurement data we get. We find out the x-axis indicate the channel vacancy length, and the y-axis indicate the probability, approximate probability. And then we can find out, yeah, the vacancy duration follow this exponential-like distribution, but we can find out two more messages we want to deliver. First of all, it can be nearly exactly estimated. Second, the channel state cannot be modeled as a first-order Markov model, okay, which has been used widely for all different papers as their basic assumption. Okay, why we can get this conclusion? Very simple, because we have the measurement data, and then we have the approximation already. So if this channel state can be modeled as a first-order Markov chain, and we can see that for this approximation exponential-like distribution, B and C, the parameters should be same. But actually, it's not the case in the measurement study. And also, if this is a first-order Markov chain, and then the current channel state will only depend on the previous one. But actually, this is also not the case for our measurement study. Okay, so this can give us a simple conclusion. We cannot simply model our spectrum usage as a first-order Markov chain. But how can we model it efficiently? We don't have a perfect answer for that. It's very sorry for this, because for different channels, we try different model. We find out you really cannot find a perfect model to feed all the channels. Yeah, sure.
Maybe I'm not 100% sure what you mean by cannot be modeled as a first-order Markov chain. Because It's like you can always model anything as anything, right?
Mm-hmm.
Model may be good or not. For example, when you say the however there, what shows to me is that at the same channel. Meaning, if I'm modeling a particular channel, I'm modeling that channel and I'm going to find the parameters for my Markov chain for that channel. But for example, in this case, however, that doesn't imply me that the model is not good, because it could be that in a channel I always flip in one and zeros, and then I have like thousands of cases where that's the case, and that would give the first slide. And other channels where I actually have more longer intervals, then the second case is what happens. So
no, actually, what we do is that because we have 1 week data even for a particular channel, and if you model it as a first order Markov chain, and then you actually, even for this particular channel with different days data you put in it, it will still cannot follow one single model. So that's the case. It's not say across all the channels. It's just for this particular channel because of this 7-day information. And you cannot use one single model to feed it. Okay, so besides give a kind of negative conclusion, we want to see some more like a promising way. So what can we do then? So we check the correlation. We want to see whether the spectrum usage have a certain correlation. So in the way that whether for this particular time, if I know the channel state, how about the next certain period of time? So this is a temporal correlation. And then also for this particular channel, if I know the channel usage, how about the channel next to it? So that will be the spectral correlation. And also for this particular channel, if I know its usage, how about the other place for the same channel? So that will be the spatial correlation. So we want to check whether the spectrum usage have any correlation in terms of temporal, spectral, and then spatial. Okay, so we want to check the spectrum coefficient, so which indicate the likeliness of these two sequences. Okay, so this is the kind of motivation for the work, and then we continue check the study. So for the channel state series, which we have already obtained just now, this is a kind of a small level measurement. It's a microscope measurement for the channel utilization. And we know that for a certain spectrum band, actually it's only like 0.2 meg. And for some service, actually it actually has a rather wide band, wide range of the spectrum usage. So we're looking at it from the service point of view. So we defined a service congestion rate, which is trying to examine across all the channels within the same service. For example, GSM 900, for example, TV band. We want to check all the channels within the same service for a particular time slot. So that's why we detail check the congestion, the service congestion rate for different service within a service, different spectrum band. And this is the information we can get. This is the one result we get for GSM 900 upper link service. And you see that we trying to study the intra-service within this GSM 900. How about the spectrum correlation? Okay, for different frequencies running in this GSM 900 service band, is there any correlation in between? So the conclusion we get, simple conclusion we get is there's a rather high correlation. Okay, so which means if you measure a certain spectrum band, the usage, you can more or less use that to help you to predict the other frequency band, the spectrum usage in other frequency band. Okay, so this is the motivation. We have the result. Then we see whether we can come out a rule, we can come out a certain way to really do the spectrum prediction. Okay. So the information we can get here is that for this different time series, we have a lot of channel. And then for each channel, we have the channel state information. For that particular time slot, the channel is busy or the channel is idle. Okay? Given those information, whether we can do some prediction. Okay? So we find out we may be able to use a kind of pattern to do the prediction. So what is a pattern? We consider a block as a pattern if it appears many times. Okay? For example, this we can treat as a pattern. Okay? After 1, if after 1, then will be a 0. After 0, then will be a 1. After 1, then will be a 1. So if we treat this as this block as a pattern, because this pattern appears many times. Okay? So if this pattern appears, for example, 1,000 times, and this pattern also is a pattern, it appears also many times, for example, 990 times, then with these two patterns altogether, we can do some prediction. If the blue pattern appears, more or less indicate the next time slot, the different channel will all be idle. Okay, so we can do this. So this actually is an idea we borrow from the database people. They have this time series analysis, and this is a frequent pattern mining. Okay, they're trying to use the frequent appeared pattern, and so as use this, you can do the prediction. Okay, so this is the idea we use. So that's why the spectral prediction will include those 3 steps. The first step, find out all those frequent patterns. And then you generate some prediction rules, and we call this as a pattern association rule. Because you have those patterns, you find out the relation of those patterns, and then this can help you to do the prediction. The last step will be simple. You just predict according to that rules. Okay? So as I just mentioned, we actually borrow the idea from the data series, time series people, and they do the research on this pattern mining, frequent pattern mining. But the uniqueness or the challenge for this problem is that this frequent pattern mining actually works in 2 dimensions. Normally, when 2 people do the data series and the time series understanding analysis of the data, like the stock market, they're normally 1-dimension information. But here, we have both time and spectral domain. So that's why this is what we call frequent pattern mining in 2 dimensions. Okay. So for this, actually, there's no existing algorithm work and in both 2 dimensions, because this is a dimension explosion problem. And the running time will be huge in the large-scale data, for the large-scale data. Okay? So that's why we need to think about the potential way to do the optimization. So the first optimization we introduce actually is a very simple idea. Say if this block is a pattern, it only come a pattern when all its sub-blocks are all patterns. Okay? So with this, we can check that for a block x times y, we need to check 2 part of x, y sub-blocks. But this is still huge if x or y itself is large. Then we come out to a second heuristic and kind of second optimization in the way that a block is a pattern only when all its parent blocks are pattern. Okay, and for each block, its parent block only 4 parent block. Okay, so in this way, we can come out a much more efficient optimization heuristic. So we apply this optimization efforts and check all this pattern mining algorithm, and we can find out before optimization, well, this problem can quickly crash. And after optimization 1, is still running time is still long. My student tried 1 day and he gave up, has to figure out a new heuristic. And this optimization 2 actually work. So this is the simple prediction result. And we can see that this is a prediction we use applied TV1 and GSM 900 upper link. And the conclusion we can get is that the prediction accuracy is extremely high when the training set is sufficient. But the training set, actually, you only need to take like first 3 hours data as the training set. Then you can simply apply for the rest of the 1 week.
Compare with simpler prediction, like just like correlation. linear correlation prediction?
Yeah, we did have. So here is the comparison. Okay, so this is the prediction result. We are trying the same training and testing set. We compare. This is the occupancy of the spectrum, and we compare our predicted the frequency mining, pattern mining to the prediction algorithm to the first order Markov prediction.
But then the first order Markov, you're just using one information. Yours, you're using many. So a much simpler algorithm to exploit the same number of data they use to predict the next one is to use just linear correlation.
No, actually, for this case, actually, we also use the first 3 hours as the training to train our model, to train the Markov model and the parameter, and then we use that to predict the next start.
Predicted just based on the last state, right?
Yes.
And on your 2D, you're predicting based on a number of states. So it doesn't seem...
And yes, in the case that we explore the spectrum dimension. But no, in terms of even for the temporal one, we actually take the similar information as input. The only difference this does not take the information across multiple spectrum bands. It is the first for the first Markov in terms of this particular spectrum band. Maybe we can discuss this.
Yeah.
For this prediction, they take a look at the prediction patterns generated by the basically programs. I saw this basically this because the sampling frequency is only 0.2 megahertz. So is it possible? It's because for the GSM band, TV band, they naturally have some kind of bandwidth which is larger than this 0.2 megahertz, which is causing this prediction inaccuracy.
No, actually, for GSM, it has a lot of spectrum subband across the same service, and for different operator, they will operate different subband. For a particular operator, it will not operate all the spectrum bands. The government will actually allocate, for example, later we come out the spectrum sharing part, the government will allocate a certain sub-bands to a particular operator, and then the other sub-bands to another operator. So then that's why we have different operator running GSM service.
Looking at the band, basically you are using it as an example, right? GSM, I don't actually expect cognitive radio to operate in that band because it's a quite busy band, I think in general. TV is actually what I expect most basically, basically device will operate, right? Yeah. And so for example, TV's correlation accuracy will be quite interesting in seeing, for example, TV3, let's say basically for that band. The first Markov prediction only have 75% basically accuracy. I'm interested to understand why it is of that. Is that because the traditional prediction miss the energy in the slot, or basically the TV's frequency is shaped in such a way that doesn't appear or something?
I think the reason why for this previous work not fit pretty well because of, again, as I just mentioned, we cannot use a simple model to fix it. And why our work can fit pretty well is, again, because we use the pattern. We find out the pattern to do the prediction. There's no particular model we are using, actually. Yeah, so I think that actually explains the difference.
So if we can graphically display the patterns, it may offer some additional information.
Yeah, sure. And this actually is continue the measurement data and then data analysis for different location because we measure in 4 location, and we find out actually those are the same service in different location, and those are the prediction result. And for this previous slides, we check all this as a same service, and then we check different services in different location. Okay, we want to see for the same location. We want to see whether there's a cross-service correlation, okay? And for example, whether GSM 900 and TV1 has any correlation, and the result is not that promising in the way that even using the frequent pattern mining scheme, you cannot find too much correlation in between. This is mainly because of the service nature. Okay, so a very brief summary about the measurement study. We conducted the spectral measurement study for 4 locations concurrently in China. And we checked the channel vacancy duration distribution. And the conclusion we get is follow exponential lag distribution, but it shows that once first order Markov chain model cannot estimate the real channel state perfectly. And we conducted the study in terms of correlation. We find out the temporal, spatial, and then spatial correlation really exist. And the intra-service spectrum correlation actually is quite high. And we further propose a frequent pattern mining scheme, and we get some interesting result in terms of the prediction accuracy. Okay? So after we have those study about the channel condition, we want to see whether we can, based on those measurement study, find out some interesting observation. Okay, so this actually comes to the second piece of work, which is spectrum sharing among multiple primary users. So as I just mentioned, we did a measurement study, and then we particularly looking at some spectrum bands like CDMA, GSM 900, GSM 1800. Those spectrum bands are occupied by 2 major service providers, wireless service provider in China, which is China Mobile and China Unicom. Okay, so they own these different spectrum bands to run the service. And this is what we call the collaboration coefficient. I will introduce what is the collaboration coefficient. And for the frequency used in China Mobile and the frequency used in China Unicom. And the result we find out, the collaboration coefficient, we defined it as a portion of the time slot when the occupancy state of the 2 channels are different. When China Mobile is busy, China Unicom is free. And when China Mobile is China Unicom is busy, the China Mobile frequency is idle. So we find that we define this as the collaboration coefficient in terms of one service provider, you are lack of spectrum, but the other service provider, actually they're free, okay? So this shows that the spectrum coefficient is high for many frequency bands owned by those 2 service providers. So the simple conclusion we can get is we have this unbalanced spectrum usage of those 2 service providers. And then we literally give the question, so how about we share among the service provider? When one service provider, you particularly are busy, why not just borrow? Why not just share this other spectrum, the other wireless service provider spectrum band? But then here is the question is, I am a certain service provider. I own all my base station. I don't want to share my infrastructure to other service provider because naturally they are my competitor, okay? So, but how about we are not sharing the service infrastructure, but just share the spectrum? We just share the spectrum usage in terms of time portion. And those base stations, you're still, if you are serve the large user demand, you are short of spectrum usage, spectrum resource. Maybe you can come out a certain agreement with the other service provider to temporarily rent or temporarily lease a certain portion of spectrum. Okay, so this is the motivation. And then we're looking at, is there any like uniqueness or challenge for this type of spectrum sharing? So first of all, the base station, they belongs to the certain group. I cannot change that. So this is my infrastructure. I don't want to share with others. So this is a naturally, okay? So I don't want to dynamic form any group. The group is there already. They belongs to different service provider. And service provider, as I just mentioned, you normally are competitor with each other. So I want to maintain a certain level of cooperation I don't want to have a tight collaboration with you because I don't want to give up my customer ownership. I don't want to give up my control power for my base station, okay? And from the nature point of view, every service provider, you don't want to unconservatively serve all your resource to other service provider. Okay, so with those uniqueness keep in mind, we find out actually group bargaining solution is a perfect model suit for this scenario. Okay, so in this case, the base station, you can still treat as individual. You form a group. Basically, you form a group because you belong to the second service provider, and then you collaborate with the other group with this under this group bargaining umbrella. And then base station in the same group, you are trying to make efforts to improve your aggregated payoff. Because from the service provider point of view, I care my own utility. So to carry out the collaboration, the service provider, you are bargaining with each other at the very beginning of each period. We set a lot of period. So at each period, at the beginning of each period, you do the bargaining in terms of whether I can achieve agreement with the other. And if I reach a certain agreement, I will do collaboration. Otherwise, I will do non-cooperative way, which is the nature way we are running today. Okay, so this actually, I will not go into the detail, but this simple umbrella, this simple problem can be solved with a centralized way in the case that a lot of information, all the information being shared among all the service provider, then I can treat this as a simple optimization problem. Simple optimization problem, I can solve it in a polynomial time with the existing convex optimization technique. But the key is I have to give up all the detailed information to other service provider. I have to share all the information in terms of my privacy, my business secret, and this cannot work well to the large-scale system. So that's why we propose two distributed algorithms. One is a local bargaining algorithm, the other is a Lagrangian decomposition problem method. So for the local bargaining method, actually it can work in a rather scalable way, and it can guarantee the convergence process. Okay, I can guarantee this process can converge in a rather fast way, but I cannot give you the performance guarantee. And also, I cannot completely protect the privacy. And the Lagrangian decomposition method actually can work pretty well in a large-scale system, and it will protect all your privacy information, and also it can guarantee a performance gap is arbitrarily small compared with the optimal centralized method. But the bad thing is it will have a slower conversion speed. So that's why we propose this two distributed scheme in terms of different scenario. You may decide which scheme to use. And this is the performance evaluation. We do some simple testing in different topology. Those are the one case, for example, those are the two service provider. All the blue base station belongs to one service provider, all the red base station belongs to another service provider. So they have some contention relation as we indicate here. So here we compare four different schemes. The breakpoint scheme is that we are not collaborating with other people. So this is a normal scheme we use today. Everybody just run in a non-cooperative way. And this is the central approach, CM, which gives the optimal solution in terms of the performance. But again, it's not scalable. It's give up all the privacy information. And this is the local, the LB is the local bargaining scheme, and the LD is the Lagrangian decomposition scheme. And you can see that the performance-wise difference, and then also the other property difference we have already described before. Okay, so those are the two typical cases we study. And finally, I want to give a short conclusion and also introduce some of other activities we are conducting. So generally speaking, for this cognitive radio dynamic spectrum sharing paradigm, there's still a big gap between have a flexible cognitive radio component building block and have a large-scale deployment for the cognitive radio networks. There's still a big gap in between. So that's why recent years we can starting see some like spectrum cognitive radio system. For example, the Victor Barr, the other people there in this group in Microsoft Research, they have already conducted some result on along this direction. And also building and deploying cognitive radio networks is a very complex task. And so that's why there are a lot of promising direction to go in terms of how to build from the component to the network. And there are a lot of policy and technology issues. They are intact together. For example, like the service provider sharing technique we proposed, whether we can really persuade the operators to really apply this kind of collaboration. Are they willing to take those things? There are a lot of policy, technology-related issues. They are intact together. And also, the cognitive network technology is not only limited to the dynamic spectrum sharing. Even without dynamic sharing umbrella, even with 4G technology, 4G standard, they are still talking. They are starting talking about the cognitive networks technology. For example, you have different spectrum. Then how can you do aggregation? How can you do the more efficient spectrum access, even without primary user and second user concept? So all those things are some promising direction to go. So in our group, actually align these three directions: spectrum policy, algorithm, and also the testbed prototype things. We are conducting some of the efforts. Okay, for example, for the algorithm part, we are starting for this all different aspects in terms of how can do more efficient sensing. How can you do the prediction-based sensing and sharing, for example, because we have already some prediction result? How can you do more efficient spectrum sharing and access? And maybe we can introduce the cooperative concept into the cognitive radio networks. So all those efforts, all those different directions we have studied, pay some efforts on that. And in terms of spectrum policy, we also have conducted several pieces of work in terms of how can we have a more efficient spectrum auction way. And if we want to do truthful but also performance efficient auction, how can we define the auction rule? And also in the future dynamic spectrum market, how can we motivate our service provider? It's not only the technology motivate them. They should find out business model. Okay, so if they can find out really they can earn money from those dynamic spectrum access, they will easily buy this concept. Otherwise, you talk with operators, say, you have spectrum not being used, why not share with others? It doesn't make sense to them. And also incentive pricing, all those kind of things are very interesting. So we are doing something along this direction. Finally, in terms of the testbed, actually, we also pay some efforts in terms of how can we build a cognitive radio testbed so as more efficiently evaluate all the algorithms we proposed. So we are spending some time in the software-defined radio testbed. This is a USRP-based testbed. So finally, is the short conclusion. I think along this direction, cognitive radio, dynamic spectrum access, there's still a lot of work to do, and it will eventually make significant impact to the future wireless network. So fundamentally, we need to have a better understanding about the spectrum usage before we're talking about efficient spectrum access. And also, we need to think about both technology and economics point of view, and because they are intact with each other. So that's why we need to kind of consider both when we think about new topics. And finally, is the real system deployment. It's not easy. It's very easy just talking about algorithm write papers, but how can we persuade operators really deploy the technology? How can we persuade equipment provider really generate, manufacture the equipment which has this capability? It's a lot of work. So that's why collaborating with industry is a definite must for the academia people. Okay, so that's the end of my presentation. Thank you.
What sort of reactions are you getting from the service providers to this research?
And actually, we didn't talk directly to service provider, but we have a lot of collaboration with the equipment provider, for example, Huawei company in China. And they have very strong interest in this technology. The reason is very simple, because there are really lack of spectrum for the future service like 4G, 5G. And they have to take this cognitive related idea, as I mentioned, not necessarily under primary user, secondary user category. Especially for the equipment provider, they're kind of saying, say, the dynamic spectrum access may be far to go, but the cognitive radio idea is a must for the future technology.
So, you're a service provider. I would imagine one of the arguments you would make is it's not so much that there isn't enough spectrum, it's just that the wrong people have it. In other words, they need it. And how do you respond to that basic argument? That we don't need any of this. All we just give us more spectrum. Take it away from people who aren't using it. I mean, you've done your studies of spectrum usage. Some people aren't using it at all or are not using it very well. Just, let's just reallocate it to the providers.
And give you an example. Recently, we discussed with Huawei. We say, well, FCC has in US have already say TV band can be used as a TV white space for the other usage, right? So suppose China or the other countries also push this direction, and then as an operator, it comes to the equipment provider, say, well, give me a solution which I can use the traditional 3G or GSM band for my service, and meanwhile, I want to also leverage the TV white space for my services. They have not of incentive in terms of talking of this. They say, well, I will still use my original band, but I want to also leverage the extra TV white space band. But how can we provide service for that? Because from service provider's point of view, they get used to the scenario that the band will be allocated to you and you can have a certain quality of service guarantee for that band. But then if we're talking about, I will actually use TV white space, no spectrum band, yeah, a lot of study shows that the utilization is low, but still has. So once the primary user back to the service, how can you leave? How can you still make your service provide a certain good quality of service guarantee? So a lot of interesting discussion along this direction.
I recall in the US, in this space, they standardize something like 3 classes of device, right? So basically, the base station actually require you to not only sense, also have a database and have basically GPS device. So basically, you are in a sense rely upon basic history and collective information to make a decision whether we can use the spectrum or not. And record basically those lower class device which doesn't have GPS that will basically require you to lower down your basic transmission powers. I think that's basically the US basically in a sense. The primary user will have basically with more high priority to use it basically channel. So for example, even some of the channel here showing 50% channel utilization. If that basically for example, if this is indeed the occupancy level of that channel, if you allow secondary system to utilize channel, will that disrupt the primary user interface? Because this backup behaviors may not be all that basically well if there's hidden terminal or other issues involved in the basically thing. You may not be able to sense basically the signal at your locations without that. So I'm wondering, how this dynamic sensing versus just basically try to be absolutely sure using, for example, time, basically easy for information. For example, in your early spectrum graph, right, there are some channels you don't sense any energy at all. During the entire 7-day period. Then using those channels is almost basically a sure thing because you're not afraid of interfering with anything. Do we really want to use very sophisticated technology to basically
So actually, this is a very complicated thing. From again, combining the policy and then technology. FCC really, U.S. part really push, actually also including Europe, push the concept as the radio map database. Okay, so I will just maintain a radio map database. Everybody, well, you just go to the radio map database to check the usage of the primary user. So in that way, we'll have a better understanding about the channel. So first of all, how to build this radio map. So there's a lot of complicated issue. You need to do the sensing, you need to do the cooperative sensing so as to avoid the hidden terminal issue, right? And also helping you build a more accurate radio map. And the other thing is that, as I just mentioned, for those spectrum bands, you want to borrow, you want to reuse. Even though their utilization is very low, but there's still some primary use ongoing. So that's why when you are an operator trying to deploy service on top of those opportunistic channel, you have to have the capability. For example, your base station, you originally deployed with a certain band, but then if the primary come back, you have to release those spectrum. Well, you do spectrum borrowing, you can borrow some spectrum from the other neighboring base station. But if you borrow from that, there will be like kind of borrowing propagation. So how can you solve that? So all those things bring some new topics for the service provider. Originally, I get used to how to do the planning. How can I plan my base station in a certain region I want to deploy service? But now you give them opportunity, which is not a permanent 100% opportunity for them. This actually brings a lot of new issue for them. Those are the issues industry, I mean the wireless service provider and then equipment provider, they are seriously looking at those issues now. So the very good thing is really seriously they are looking at those issues from the deployment point of view rather than the paper kind of work.
I think I mentioned that I like the idea of the dynamic spectral allocations a lot for a different application. So here's my question. It's like, it looks to me, when you look at cooperation between service providers in the same service, I think what's good is that that's a very important market which has a lot of demand, and it's like if you can optimize anything, that's a great game, fine. But at the same time, my impression is that the distribution, if I have two cell phone providers, the distribution both in terms of time and geographical location of those two populations are essentially the same. And the spectrum is free until I saturate. Like, so it's like, yeah, most of the time it may be empty and I have empty holes here and there, but that doesn't matter. The only place it matters is when I'm saturating, I'm at capacity. And I would expect that when I am at capacity at a certain geographic region, my competitor is also at capacity at that same region. And if I can borrow from neighboring cells, it's like I can borrow from my own cells in the neighboring. So what exactly can you actually do anything? I guess that's the question.
Yeah. Actually, that's also the question for us when we first see the measurement result we get. We are interested in seeing why those results can really exist in the way that we think about GSM as such a crowded service already. Why China Mobile and China Unicom has such a kind of distribution in terms of their spectrum usage. We actually trying to check for the service provider, but it's very pity they kind of confidential information they cannot distribute and disclose to us. But I think why we're still interested and then talking along that direction, I think first of all, we really get those measurement data. I think it's nice to disclose it. Second, even this not apply for GSM 900, there's still such an opportunity exists for different spectrum bands, right? Running among different service providers. Then it's still, again, naturally to share the resource. But again, service provider, they are competitors, so they don't want to give you too much information, but just in such a way how to do the resource exchange.
Thanks, Professor Zhang, for the excellent talk.
Thank you.